Hello everyone, this is Zoe Winston and this is my presentation for the Foundations of Math midterm. So to start, we're going to go through our agenda, so I'm going to go over an introduction to what proofs are, and then talk about how proofs are different, and then go into a step-by-step process of how to go through a proof, and then show the clean proof for the proof I'm using as an example for this presentation. So as an introduction, proofwriting is an So the thing about proofwriting is that you have to show why something is true. You can't just show that it is true. So there's no solution, alright? There's multiple different ways to prove anything. Anything worth proving is worth proving multiple ways, and so we can go through different types of proofs. There's different inductive proofs, there's different direct proofs, proof by cases, etc. There's so many different ways to show that something is true, and there's no one solution. There's no 2x equals 4, therefore x equals 2. There's no correct answer like that. And additionally, showing something is not the same as proving it. You can show something's true, but that doesn't mean it's always true. So we don't know, by looking at an example of how something could be true, we don't know for sure that it is true. So proving is really a test of your mindset of how you can go about showing that something is definitely, always, in every case, true. And so previously we took rules for granted, so we would see things like De Morgan's law in electrical engineering, right? This course, it teaches you to ask why those things are true. How do we know those things are true? And how did we come to the conclusion it's true? So, as a continuation of how proofs are different, I will show you some examples of how my mindset was changed by proofs. So, for proofs, we have to solve x squared equals 2. Right? So we know x is going to be plus or minus the square root of 2. Now, they would ask, is this number rational? The answer is no, right? The square root of 2 is an irrational number. However, in this class, we ask, what does rational mean? What does irrational mean? How do we know for sure a number is irrational? And how do we prove this, right? What is the definition of irrational? How do we fit the square root of 2 into this definition and show that it is definitely irrational? We can also go into different areas of mathematics. So we talk about combinatorics, we talk about graph theory, we talk about set theory. So mathematics can be shown through proofs connect everything and help us define the different rules, theorems, and lemmas that define these different areas of mathematics. So combinatorics, for example, we're given 3 cadets, right? So how many ways can these 3 cadets sit in 3 different chairs? So here I have listed for you 6 different ways that these cadets can sit in these chairs. And we know that there are no other ways because other than that, it would be repeating one that's already listed there. So in terms of how we can look at this from a proof's point of view, how do we know this, right? So how do we know for a fact that there are 6 ways to make 3 people? What's the general rule? How do we apply this to a broader population? We don't only care about 3 people. What if we have 300 people? Are we supposed to list every single combination? So from this example of 3 people, we need to work to derive a rule. So for 4 people now, right? Once we've placed the first cadet of that 4, now we have 3 cadets left over and 3 chairs to sit in. But we've done this example before. In the proof on the slide before, not the proof, the example on the slide before, we showed that for 3 cadets and 3 chairs, there are 6 different ways they can sit. Alright, but now, first cadet in the first chair, okay? Now there's 3 people and 3 chairs. So we know that for that specific set where you have 1 person in the first chair, there are 6 more ways to do that. But that was just putting the first cadet in the first chair. What if we put the second cadet there, or the third, or the fourth? So that shows that there's 4 different combinations, and then from each of those 4, we know that there's 6 ways in each of those groups that we can set these people up. So we know that we have 4 times 6 is 24 different ways to arrange 4 people in 4 chairs. But, again, how do we make this a rule? So as we can see, this example specifically, we had the 4 times the 6. And in the previous example, using trees is typically how we would show this, but just to make this a more condensed version, we're using 3 times 2. So this is going to make a factorial where we'll have 4 cases times the 3 cadets from the previous one, times 2 cadets, and then there's 1 missing. Because every time you see a cadet down, there is 1 less cadet to see and 1 less chair to fill. So we can now see how each level builds off of each other, right? When you add 1 more level, you have that many more combinations of making the previous level. So the proof we're going to do based off of this is that we'll have, for k plus 1 be k factorial ways to arrange the remaining people once that k plus 1 person is seated. So therefore we know that there are k plus 1 factorial ways to arrange k plus 1 people. So this kind of thinking shows how proofs are different, right? Before proofs, we would just say, okay, we want to know how many ways to sit 4 people. We're putting people at a table. How many different ways can we do that? Now we have to show definitely what the rule is for sitting any number of people in any number of chairs. And it goes understanding of why something is true rather than just finding the correct answer. So the proof method, how do we go about proving things? So for our process, we're going to have a 7-step process. So step 1, we're going to develop examples. So this is really getting in, trying different ideas, trying different cases. What could be true? Is it positive? Is it negative? Are they subsets? Are they disjoint sets? Etc. And if the statement is not true, we can redefine what the statement we're proving is, right? Because if the statement's not true, you cannot prove it to be true. So we have to find something that we can prove to be true, whether it's a limit on the sets of the function, whether it is saying that instead of the 2 sides being equal, one side is a subset of another. Step 2 then, we're going to develop our if-then statement. So once we've determined something that is true that we are trying to prove, we have to develop our if-then statement. So this is saying, what exactly are we proving? Alright, so given what, we are trying to show what. And by structuring it as an if-then statement, we make it extremely clear for ourselves what we are trying to show and what we're working with in order to show that. Now, steps 3 and 4, I combined here on this PowerPoint because they're related. And so for step 3, we're going to identify your no. So based off this if-then statement, we're given a if, then this other thing must be true. So that first statement between the if and the then, so the thing that we're taking for granted, that is our no. That is what we are working with to prove the other half of the statement. So step 4 is now going to be expand that no as much as possible. So really getting in there, using our definitions, trying to make it as expanded as possible so you have as much to work with. Step 5 and 6, we're going to be identifying our show. So here we want to expand our show as much as possible in step 6, and it's the same idea. The show is what comes after the then statement. So from working with the no, we have to manipulate it and use our definitions, expand it in order to arrive at our show. So by expanding our show, we hope to come up with a statement as similar, as closely related to the expanded version of the no as possible, so that we have a goal, a clear goal to work for other than just the initial show. Now step 7 is going to be writing that final if-then statement. So from your expanded no and your expanded show, you are then going to rewrite that as if our no, then our show. And this gives you a final statement to work with for your proof that you can start your proof off with. Now, as an actual example, the statement I was assigned to try to prove was that the power set of A union the power set of B is equal to the power set of A union B. Now, to be clear, the power set of A is defined as the set of all subsets of A. Alright, so our first step is to develop examples. So first we define our universe, right? So what if X equals the set of 1, 2, 3, and 4? Now we're going to define A as 1 and 3, and then B as just 3. So then, by the definition of union, our union there of A union B is going to be 1, 3. Now we're going to set the power sets, right? So the power set of A is the null set, 1, 3, and 1, 3. Well, the power set of B is the null set and 3. And now, as you can see, when we union those two power sets and take the power set of A union B, we have 2 equal sets. So as you can see here, these are 2 equal sets, which is showing that this example is correct. But, as I mentioned on the introduction slides, showing something is not the same as proving. So we need to try to get in here and try to find an example that shows that this is not true. Now, if A equals 1, 3, and B equals 2, so as you can see in this previous example, B was a subset of A. So here they're disjoint. So A union B is going to be 1, 2, 3, and our power set of A is going to be the null set 1, 3, 1, 3, and the power set of B is going to be null set and 2. But when we combine these two in the union versus taking the power set of this union, we can see that they're not equal, right? The set 1, 2 is not contained within this union. Same with the set 2, 3 and the set 1, 2, 3. So that every element here is contained within the power set of the union. So what we can conclude is while this initial statement of power set of A union power set of B equals power set of A union B is not true, we do think that we can show power set of A union power set of B is a subset of the power set of A union B. Alright, and as we can see back here, these are equal, which means that this statement holds true because it's still a subset even if they're equal, because it contains only elements within that other set. Now, step 2 is writing our if-then statement. So, we have decided that we are going to prove power set of A union power set of B is a subset of power set of A union B. Right, so that is what we're trying to prove in this statement. Now, we extract the statement that we are trying to prove. So that is what we were trying to prove, but now we have to frame that in a way that we can talk about it and we can dig in there. Show is. So how we're going to reword that is, if X is an element of the power set of A union the power set of B, then X must also be an element of the power set of A union B. Now, we're going to identify our no from that statement. So as I talked about, the no is going to be the statement between if and then. So that's our givens and what we have to work with in this proof. So we know X is an element of the power set of A union the power set of B. Now, by the definition of a union, if X is an element of the power set of A union power set of B, then we know that X is an element of the power set of A, or X is an element of the power set of B. Now, the power set is the set of all subsets of the set. Alright, so what this means is that if X is an element of the power set of A, then X must be a subset of A. Right, so since we know X is an element of the power set of A, or X is an element of the power set of B, we now know X is a subset of A, or X is a subset of B. Now, by definition of a subset, for every Y element of X, Y is also an element of A, or it's an element of B. Alright, so this is our expanded no, is that we went from knowing that X is an element of power set of A union power set of B, to for every Y element of X, Y element of A, or Y element of B. So this shows that by expanding our no, we're really able to get more information out of the statement. We're able to break it down to its baser level. Now, write down your show. So, again, from the if-then statement, we take the stuff after the then. So here we have X element of the power set of A union B. Now, by definition of a power set, the same way we did this for the no, if X is an element of the power set of A union B, then that means X is a subset of A union B. And by definition of a subset, X being a subset of A union B means that X is the set of Y in the universe X, such that Y element of A or Y element of B. Now, taking these expanded no's and shows, we go from X element of power set of A or X element of power set of B, then X element of set of A union B. And then that becomes, if X is a subset of A or X is a subset of B, then X is a subset of A union B. Alright, now this statement seems a lot easier to tackle, right? We go from using power sets, which is something we haven't necessarily worked with as much, just working with sets and unions and subsets. So this seems to be a lot more wieldy, and we are able to get a better grasp of what exactly we're trying to prove. Now, here's our final proof based off of these sets. So, as I talked about, we're going to start off this proof with our expanded if-then statement right here. So, we know that A and B are sets. Alright, so if X element of power set of A or X element of power set of B, then X is an element of the power set of A union B. Now, by definition of a power set, if X is an element of power set of A, then X is a subset of A. And thus we now know that X is a subset of A or X is a subset of B. Right. Now this may sound super confusing so far, but all we've done here is we've taken our expanded if-then statement, and then we are going through how we expanded our no. So as we went through in step 4 of expanding our no, I'm going to dig into that given and identify what information we know from them. Now, by definition of subset, the same way we did this earlier, if y is an element of x, then y must be an element of A, or y must be an element of B. And thus, y must be an element of A union B by definition of a union. Now, going back and using that definition of subset again, we know that if y is an element of x, then y is an element of A union B, implies that x is an element of A union B. Okay? Now, this is again by the definition of a subset. Now, we have our given rewritten. So now our given states that x is a subset of A union B. And thus, we know that x must be an element of the power set of A union B by the definition of a power set. Now we have shown what we are trying to prove. We have shown that if x is an element of the power set of A union power set of B, that x must be an element of the power set of A union B. So this concludes our proof, and as you can see, we broke these down specifically into 7 different steps, and then used those to create our final clean proof. But you can see none of the labor that went in here. You can't see the examples that we went through, the confusion, the original statement that we had that we were trying to prove that we showed isn't always true. All you see is the simple proof for the statement we arrived at as being true. Thank you for listening to my presentation. This concludes my brief. Pending any questions. Thanks again.